Hello everybody. First of all, excuse my English. Unfortunately, it's not as good as I would like it to be, and maybe some words would be were translated into English incorrectly from Russian. But anyway, I will try to do my best, and I will try to explain everything that I have in this presentation. So the idea of this presentation and this webinar, which I am offering to Asahi, is to make an overview of the processes that goes after the synthesis and the equipment that we need for these processes. The processes that occurs after the synthesis are pretty typical. So first of all, of course, this is the filtration. The second is drying, and third is evaporation or distillation, whatever you call it. So let's start from the filtration, which is a pretty typical application in a lab. So that's how it all started. I've read in Wikipedia, as far as I remember, it started something like 150 years ago when Buchner and Bunsen developed their funnel, funnel and the flask, and so they stayed together after that for more than 150 years, and something tells me that they will stay together forever and ever till the end of times. I think everyone who is a chemist at least once in a lifetime saw these standard lab equipment in the lab, and even maybe use these tools for the filtration. Indeed, this is the very useful tool in the lab, but of course it has some disadvantages. It can be used for simple applications, but sometimes we need something more advanced than the equipment that you saw on the previous slide. So when do we need Notch filters, Druck filters, and filter dryers? Well, first of all, let's define what is a Notch filter and what is the Druck filter. Notch filter is the equipment that is used for filtration under vacuum. Druck filter is the equipment that is used for the filtration under pressure. And the filter dryer is the equipment that can not only filter but also can dry the sediment that you just filtered. So when do we need them? So basically that's the list of the disadvantages of the equipment of the standard funnel and the standard flask that you saw on the previous slide. So first of all, we need the Notch or Druck filter and filter dryer when we need to protect the apparatus from dangerous vapors. Of course, when we're talking about the filtration of 100 mils of slurry in acetone, it doesn't make any extreme. It is not that extremely dangerous. But when we're talking about the filtration of the slurry with the total volume of, let's say, 10 liters or maybe 50 liters, then smelling the vapors of acetone can be pretty dangerous. And what if we're filtering something which has hydrochloric acid? This is extremely dangerous. So this is when we need some special equipment. Oh yeah, by the way, I forgot to mention that Notch filter and Druck filter, as well as the filter dryer, differs from a standard filtration funnel with one very important point. It is the lid which every one of the above mentioned units has. So this is very important. So first of all, we need Notch filter, Druck filter, and filter dryer. We need them when we need to protect the apparatus from dangerous vapors. Second point. So we need to protect the apparatus from dangerous compounds. Sometimes we filter from something that is, let's say, pretty safe, like water maybe, but the sediment that remains after the filtration can be dangerous. That can be some kind of, I don't know, cytostatic compound. So it is important to protect the appurator from this dangerous compound. Third point, we use this equipment when we need to protect compounds from the apparator's exposure. So sometimes you are filtering something very expensive, like, I don't know, API or something like that, and you're afraid that some kind of a dust can, some kind of, or I don't know, an apparator can spoil something during the filtration. So that's the third point. The fourth point, when you need to protect the compounds, the sediment that you're filtering from the contact with the ambient atmosphere. Either that's because of the compound can react with, for example, the oxygen that is in the atmosphere, or maybe you are afraid that some dust from the atmosphere can sediment on the compound or something like that. So this is another point. The fifth point is when you need to load slurry under vacuum. So when do we need that? It is very easy to operate with a funnel when the funnel is relatively small, and for example the reaction mixture is the volume of the reaction mixture is relatively small, like for example 100 mils or 200 mils. But when we're talking about, let's say, 10 liters or 50 liters or even 100 liter, you cannot just take a flask with your hands and rotate it above the filter and discharge the flask straight onto the filter, because the weight of the 50-liter reactor is much bigger than the weight of the of a small flask. So in this case you need to load somehow without rotating the vessel, and you can do it under vacuum. I will show you an example of how it is done at one of our customers' site. That's one of the projects that we successfully realized and installed in the end of 2019. Next point is when you need to do a hot and cold filtration and replacement washing. We cannot do that in a Buchner funnel because it doesn't have a jacket. So we need something special, some special equipment, some special tool that will allow us to do this kind of very important step. And last but not least, drying of the sediment. Of course, you cannot do this in you cannot do this in a Buchner funnel. Well, to some extent you can do this. Well, you can just, when after the filtration you can take out the Buchner funnel and put it into the drying oven. Yes, you can, but it is not that good because you need to take the funnel to well, first of all you need to have the drying oven, then you need to take out the funnel, you need to put it in the oven, you need to be sure that the compound won't be damaged by the atmosphere, you need to be sure that the vapors of the remaining solvent or something else that is inside the sediment, the wet sediment, will not get into the reaction with the stainless steel, that is a stainless steel chamber of the drying oven, and so on and so forth. These kind of things that create some more questions and problems than the real result. So what kind of equipment Asahi offers for to solve this kind of problems, to answer this kind of questions? Well, first of all, there's the filter reactor. Second type of equipment is the Druck filter. Asahi actually calls it the Nuch filter, but according to my experience, as we are talking about the filters that can filter under pressure, and that is very important advantage of the equipment that Asahi offers. Most of the customers that I used to meet not only in Russia but also in Europe, they call the equipment for filtering under pressure the Druck filter. So I would suggest to call it the Druck filter in order to avoid any kind of misunderstanding, because notch filter is something that can be used for filtering only under vacuum. And so the third type of the equipment is the filter dryer, which actually is the combination of the Druck filter and the heated bottom. But we will talk about this later in the presentation in details. So these three types of the equipment can be used for different kind of applications. So filter reactor. In general, it is called the filter reactor, and so as it is called the filter reactor, it is expected to be something to do the reaction, the synthesis of something. But apart from the synthesis, which can be obviously done in this filter reactor, we can also do the filtration, and we can also do the extraction, which are very important and very popular processes that are taken in the labs. Druck filter, this is pretty simple. So, oh well, yeah, of course, when we're talking about the filter reactor, this is the equipment that can be used only under vacuum. So when we're talking about the Druck filter and filter dryer, both of these units can be used under pressure. So we can filter under pressure and under vacuum, of course. And in the filter dryer, we can also dry. So what is important when we're choosing a proper filter? Well, you need to answer some questions when you are choosing a type of the equipment you are going to use. So first of all, we need to know the volume of the slurry. This is very important because according to the volume of the slurry, you will choose a proper filter. You will also need to know the volume of the sediment, and this is very important. Why? Well, first of all, let me explain what is written here for these points of fill. First of all, rule of thumb is that the height of a sediment shouldn't be higher than 1/3 of the filter height. But particle size is very important as well. We will talk about this a bit later. So why 1/3 of the filter height? This is, as I said, kind of a rule of thumb. So when you are filtering, if you will have a higher filter cake, the filtration process will be too slow. But as I said, the speed of the filtration really depends on the size of the particles, because if the size of the particles are relatively big, like 100 microns or maybe even bigger, then of course there will be no problems with filtering at all. Well, it's not only about the size of the particles, but it's also about the physical and maybe even chemical interaction that can occur between these particles. Because if the particle size is like 100 micron, but they stick together very well, forming a very dense filter cake, then again you will have some problems. So this is something that you need to experiment with, and then you will understand what is the filter cake height that you can allow yourself to do the filtration quick enough. So when we're talking about the volume of the slurry and final volume of the sediment, of the solids that remain after the filtration, it is very important to keep in mind the ratio. Why I'm talking about that? From time to time I get the calls, and this is the real story. So once I had a call from a customer, and he was saying that he's looking for a filter with a volume of 300 liters. I've asked him, why, what are you doing? This is actually one of the most, or maybe the most important question when you're talking to the customer. What are you really doing? Because according to my experience, at least in Russia, a lot of the customers think that they know what they need, but they really don't. So going back to that request. So the customer said that he needs a filter with a volume of 300 liters, and I've asked her actually, there was a lady, I've asked her, what are you doing? And she told me that we have a 1000 liter reactor. We dissolve some API in water, and we do the filtration after that in order to get rid of some dirt that is in the solid API that we are dissolving. So I've asked her what is the volume of that dirt, those small particles, and she said that the total volume of the dirt is something like maybe 300 milliliters. So the volume of the sediment is very, very low, very, very small. So I told her that there's no need for purchasing 300 liter filter. You can easily purchase 5 liter filter, but it should be a Druck filter, pressure filter, and you can easily pump all of your mixture through this filter. Of course, it should have a relatively big surface area in order to do the filtration really quickly. This is one of the solutions that we can offer to the customer, or we can offer her a cartridge filter, which is another option. So it is always very important to ask the customer, what are you really doing? Not only asking what type of the equipment you need, but to ask him, what are you really doing? So point number 3, what is important when choosing proper filter? Solvent. This is very important. So it's actually not only about the solvent, but also about the type of the compound that you're filtering, because you need to know the chemical activity for both, for the solvent and for the compound. And for the solvent, you also need to know the boiling point. Well, I think it should be pretty obvious why we need to know the chemical activity, because you need to know that in order to choose the proper material for the filter itself, and also for the material that is used for the filtration. Filter tissue, filtering paper, and so on and so forth. There are some questions. There are some questions about that. What kind of filter tissue you can use, and I can give you one of example. One of our customer is working with methylene chloride, and in this case he cannot use the polypropylene filter because it swells in methylene chloride, and in this case, when it swells, the size of the pores gets smaller, and so the filtration process slows down. So it is important to always keep in mind the chemical activity of the solvent of the compound. Why we need to know the boiling point? Because if you plan to do the hot filtration or drying after the filtration, it is pretty obvious that you need to know the boiling point, not to overheat the not to be sure that you are heating it up to a proper temperature to evaporate the solvent. Particle size. Again, rule of thumb is that the particle size for this type of the filtration, the particle size should be bigger than 5 microns. In this case, you will be able to choose relatively easy a proper filter. When we're talking about the particle size in the range of 1 micron to 5 microns, there are some questions about that. And I mean, it is not that obvious either you will be able to do the filtration with a relatively reasonable speed or not. Again, this is something that will require the additional and additional experiments to be done before purchasing or before selling, before purchasing a filter, this type of the filter. And last but not least, definitely not least, how do you plan to discharge the product? Because again, when we're talking about the simple stuff, small processes like 100 mils of the reaction mixture, you can easily discharge it with your hands onto the filtration funnel. But when we're talking about the bigger volumes, then it becomes a problem. You need to do that somehow. Okay, so before we will, there is another important point that we need to talk about. It's the comparison of the filtration under vacuum and filtration under pressure. It is always very important to keep these points in mind because there are some advantages and disadvantages for both of the processes. So filtration under vacuum, what are the advantages? The equipment for the filtration under vacuum is relatively cheap. Just as you saw on the first slide, that's the Buchner funnel and Buchner funnel and Bunsen flask, and of course that costs you, I don't know, 20 maybe 40 euros or dollars, whatever, in total. But that's the simple thing. But that's anyway, in the end of the day, it's the filtration under vacuum. And another advantage is that for you need just a filter, receiver, and the vacuum pump. The vacuum pump can be found almost in every lab, so you don't need to buy a vacuum pump, and you can save some money. And as I told you, you can do the filtration even that in a simple equipment like a simple filtration funnel and the flask, receiving flask. But there are some disadvantages. Even when we're talking about the complicated units like filter reactor, which has a jacket, which has a lid, and so everything is isolated from the atmosphere, you still have some disadvantages. First of all, the efficiency, the filtration speed. The filtration speed is relatively low because maximum pressure drop that you can get when you're filtering under vacuum is 1 bar. As we talked about that, as I mentioned, the point, the pressure drop, it is. I think it makes sense to explain what makes the filtration process to go. When we're doing the filtration under vacuum, we create the vacuum below the filter, and above the filter we still have the atmosphere, which presses on the slurry, and as soon as we have the pressure drop, the atmosphere presses on the slurry, and that's how the filtration is done. Pretty simple. I think most of you, I hope every one of you knows that, and so there's no need to explain that in more details. So as I told you, the maximum pressure drop is 1 bar, because you can create, theoretically you can create the maximum vacuum, which is 0, but of course you will never reach it, and in a standard lab the maximum, relatively standard vacuum that you can get is something like 10 millibars. It makes no sense actually to go deeper, because the additional pressure drop that you will get will not really influence the filtration speed. So the second point, but it is really very important, you will always have problems with the filtration from low boiling solvents like acetone, ether, and so on and so forth, because they will start to boil even at a very small pressure drop. So when you start to create the vacuum and you are filtering from acetone, it starts to boil at about 300 millibars, which means that you will get a pressure drop of, let's say, roughly 700 millibars. When you're filtering the ether, you will have at room temperature, it will start to boil at roughly at about 600 millibars, which means that you will get a pressure drop of only 0.4 bar, which is a very small pressure drop when we're filtering something very dense or with a particle size, with a very small particle size. So this can create some problems. So these are the disadvantages. Filtration under pressure. What are the advantages of the filtration under pressure? Well, first of all, high efficiency due to a high pressure drop. Because when I'm talking about now, I'm talking about the general stuff. So I'm not talking about the characteristics of the filters from Asahi. I'm talking about the general things. So when we're talking about, for example, a stainless steel Druck filter, you can have a pressure up to 6 bars, which means that you will get a pressure drop of 6 bars. Any solvent can be easily filtered without boiling because you are filtering under pressure, which means that there is no vacuum, and so every solvent that is not boiling at a room temperature can be easily filtered without boiling. And last but not least, you can use any vessel as a receiver. For the filtration under vacuum, the vessel that you use as a receiver should be used under vacuum, because you're creating the vacuum inside the receiver in order to make the solvent get into this receiver. When we're talking about the filtration under pressure, there's no need for that. You can use just a standard barrel and put it under the filter, and that's it. The disadvantages. Well, it is pretty expensive equipment, obviously, because it can be used under pressure, and it is used under pressure. So it should be more durable, and of course it should have some protection, like pressure relief valve and pressure gauge, and so on and so forth. So that's why it makes the equipment relatively expensive. And you will also need a compressed air line or compressor. And the disadvantage is that you need to buy it. Either you need to buy the compressor, or you need to have a compressed air line in the lab. That of course depends on the lab. Some labs have the compressed air line, some labs don't. So let's get to the product overview. How do we solve these problems with the help of equipment from Asahi? Filter reactor. There are there are two types of. First of all, there are two types of the units. We'll start with discussion about the benchtop units, and then I will give you a brief overview of the pilot scale. So the benchtop units, there are 4 types of them. The filter reactor has the 4 sizes. There are 1 liter, 2 liter, 3 liter, and 5 liter filter reactors. All of them can be done either without a jacket, or they can be jacketed. And what is important is that they are fully jacketed. Unit can operate at vacuum, at full vacuum, and up to atmospheric pressure, but what is important to mention that it can hold a slight overpressure of 0.4 bars. Maximum pressure in the jacket is standard for this kind of glass equipment, and it is up to plus 0.5 bar G. Operating temperature for the filter reactor is -40, from -40 up to 200 degrees Celsius. The delta T, this is an important thing because this is the unique thing for the glass equipment from Asahi. Let me explain it. What is the delta T actually? Why we're talking about that? I think everyone from childhood remembers that you cannot fulfill a glass with hot water. Why? Because it will crack. Why is it happening? Because the because the coefficient, the heat transfer coefficient for the glass is very small. So when we pour a hot water into the glass, one side of the glass, which is washed now with the hot water, with the boiling water, has started to expand very quickly. But the problem is that the thickness of the glass doesn't allow the heat to pass through the glass to the other side of the glass and to start the same expansion on the other side of the glass, which is in contact with an air. So due to the heat transfer coefficient, the expansion on the hot surface occurs very quickly, and the expansion on the cold surface, which is cold because the heat doesn't pass through the glass quickly, doesn't occur at all, occurs very slow, very slow. So in this case, that's how the crack actually appears, because on the one side the glass expands, on the other side the glass doesn't expand. So this is the problem, and that's why all of the other manufacturers, they've learned how to deal with this, but to a very certain limit, which is 50 degrees for the double-walled reactors. So it means that when, for example, you have a double-walled or single-jacketed reactor, and you have something with a temperature of let's say 20 degrees inside the reactor, the reaction mixture, for example, the maximum temperature of the heat transfer fluid which you inject into the jacket can be maximum either can be either minus 30, that's the lowest temperature, or it can be plus 70. So in this case we keep the delta T of 50 degrees into both directions. For the Asahi glass, for the glass manufactured by Asahi, you can have the delta T of 110 degrees, which is really great, because in this case you can, I think again, this is something that it is pretty obvious and doesn't need a very special explanation, but I think everyone should understand that the higher the delta T you have between the heat transfer fluid and the temperature of the reaction mixture, the quicker you will either heat it or cool it. So this is really great, because when you have something that you need to heat quickly or you need to cool it down quickly, you can easily do that. It is not a straight correlation between the delta T and the heating or cooling speed, but roughly we can say that we can do this, again roughly we can say that we can do this at least 1.5 times quicker, or in some cases up to 2 times quicker. We can do the heating or cooling up to 2 times quicker than with the glass reactors from other manufacturers. So this is very important thing, although it is mentioned just in 2 small lines. So as mentioned already, when do we use the filter reactor? What can it be used for? It can be used for solid phase synthesis, for the extraction, and for the filtration under vacuum. It is very important to explain to the customer that when we're talking about the filter reactor, we can do only one type of the synthesis, and it's the solid phase synthesis. Why? Many, or I would say most of the customers, when we see the name the filter reactor, they think, oh, that's a cool unit, I can do the synthesis inside the reactor, and straight in this reactor I can do the filtration. No, it is not like that. Why? Because if we're talking about the synthesis that needs the filtration afterwards, it means that some kind of process occurs in the reactor, and we will get some solids after the reaction. Or we use, for example, solid catalysts. So What kind of problem we'll have then? As we have the filter that separates the upper part, which is in here, where we have the most of the reaction mixture, and the lower part, which doesn't have a zero dead space volume due to some grooves that we have in this PTFE filter bottom. So then the reaction will occur in the upper part, in the lower part, and what is the most important, it will occur also in the filter itself, in the filter tissue, filter material. So it will be completely choke up. I'm not sure if that's the right word, but what will happen, the crystals of the media will be formed inside the filter, which will obviously leads to the fact that there will be no filtration at all. And if we're talking about the filtration with a solid catalyst, then the catalyst obviously again will be only above the filter, and below the filter, where we will also have the reaction mixture, there will be no catalyst. It means that there will be no reaction below the filter. So again, you will have some problems. So again, this is important to explain this to the customer and to be sure that they are not purchasing the filter reactor for doing this kind of the processes. But as I already told you, you can do the solid phase synthesis inside this reactor. I'm not quite sure if you are familiar with this kind of things, but the solid phase synthesis itself is, I would like to explain. I would try to explain this to you in a few words, and if there is somebody who is interested in this kind of processes and maybe even do this kind of process, you can easily get in touch with us, and we will talk with you about your process in more details, and we will explain to you how can this filter reactor can be used for this kind of processes. So what is the solid phase synthesis? Pretty typical application is to synthesize the peptides. What is the advantage of the solid phase synthesis against what is called the wet chemistry? When we're talking about the synthesis of the peptide, the peptide itself consists of amino acids. So when you need to to synthesize the peptide, which consists of, for example, 4 amino acids, you need to take amino acid number 1. You need to do the reaction with the amino acid number 2. So you will have the dipeptide. Then you need to purify the dipeptide. You need to separate it from the peptide, from the amino acid number 1 and amino acid number 2. You need to take the purified dipeptide and do this reaction of it with the amino acid number 3, and so on and so forth, up to the moment when you get the peptide with the desired length, with the desired amount of amino acids. What is the problem of this kind of a wet chemistry, which can be done in a standard glass reactor? The problem is that you need to always purify the peptide, the small peptide, dipeptide, tripeptide, and so on, before you will put it into the reaction with the other amino acid. This is sometimes very difficult and takes a lot of time and energy and so on, and the efforts. So solid phase synthesis was used for this kind of synthesis for quite a long time, and how it is done. There is so-called solid phase, which is usually that's the polymer, for example, something like a polystyrol or something like that, which is this kind of polymer is that's the particles of this polymer with a size of, I don't know, 100 microns or maybe 200 microns, depending on the type of the polymer that you are using and so on. And it is chemically modified, so it has some kind of so it looks like, let's say, a head with a lot of hairs on it. The hair is the modified radical. And what you do is you put this polymer inside this filter reactor. As the size of the polymer is, the particles of the polymer is relatively high, so they do not get through the filter. So first of all, you add the amino acid number 1 to this to the reactor, inside the reactor, and amino acid gets into the reaction with those radicals, the hairs that are on the surface of the polymer. Of course, you add an excess of the amino acid in order to cover all of these hairs, all of these radicals with the amino acids. So it is very important. You do the synthesis and then you filter the excess of the amino acids, amino acid number 1 that didn't get into the reaction with those hairs. Obviously, there will be some excess of the amino acid because you added the excess of the amino acid more than the amount that is required to cover all the hairs. Then you add the excess of the amino acid number 2. That's the very simple explanation because there are some protection groups and so on and so forth, but I don't want to get into more details with that. So you add the amino acid number 2. Excess of the amino acid number 2, and excess of the amino acid number 2 gets into the reaction with the amino acid number 1 that is already we call it sewed on the surface of the polymer. So amino acid number 1, as I told you, reacted, well, the other way around, amino acid number 2 reacted with the amino acid number 1. As we added the excess of the amino acid number 2, we expect that all amino acid number 1 reacted with amino acid number 2, forming the dipeptide. So then we filter the amino acid number 2. Then we add the amino acid number 3, the excess of the amino acid number 3. And we repeat it as many times as it is required, adding amino acid number 4, 5, and so on and so forth, until we get the desired length of the peptide. As you can easily understand, when we add the excess of the amino acid and all amino acid, the previous amino acid reacts with the next amino acid, there will be no byproducts in this kind of reaction, and so you do not need to purify what you get inside the filter reactor. And this is really great. And in the end, actually, in the end of the process, by adding a special chemical reagent, you kind of cut the peptide that you got on the surface of this polymer, and the size of the particles of the peptide are very small, so you can easily filter them, and you will get the polymer, you will have the remaining polymer inside the vessel, and you will get the solution of the relatively pure peptide in your flask after filtration. So that's how the solid phase synthesis is done. I do hope that I explained it pretty clean, and as I told you, you can easily get in touch with us, and we can talk about this in more details, about the automation of this process, how you can control that, and so on and so forth. There are different kind of equipment for that. Extraction. Filter reactor can be easily used for the extraction. For example, you want to extract something from the leaves from grass, from leaves of a tree or whatever. You cut the leaves into relatively small particles, you put the leaves inside the vessel, and you add, for example, the ethanol, and then you just simply mix them with an overhead stirrer. After doing that for a certain period of time, you just simply filter everything, and so the leaves will remain inside the vessel, and the extract that you will get in your receiving flask. Great unit for a very standard application. And of course you can do the filtration under vacuum. So you can load the slurry inside and you can do the filtration. You can even do the hot filtration because you have a condenser. And you can add some solvent by means of this dropping funnel. You can control the temperature, if you're doing a hot filtration by the temperature sensor. So That's very simple and very standard. And I would say that when we're talking with the customer, let's be honest again. I would like to be absolutely honest with the customers. Uh, First of all, of course, I offer a Druck filter that is manufactured by Asahi. But as I told you, Druck filter is relatively expensive comparing to the filter reactor. And for many applications, customer is pretty satisfied with the filtration under vacuum, because either he just he filters from water, or he filters some something with a big particle size, so he can easily do the filtration and the vacuum. And so in this case the filter reactors use perfectly. Druck filter. The capacity of the Druck filter is the same. So we have the models with a volume of 1, 2, 3 and 5 liters. There are two types of the vessels. They are single walled and jacketed vessels. So when you do not need to perform the filtration and cooling or heating, you can easily purchase the vessel without a jacket. Or when you need to do the filtration, hot filtration or cold filtration, you will have to buy a full jacket vessel. I personally always recommend to buy a full jacket. The price difference is not that high, and when you will need, of course, you can do the filtration without heating or cooling in a full jacket unit, and when you will need it, and if you have only a single jacket vessel, you will need to buy well, not single jacket, you have a single walled vessel, you will need to buy another vessel for doing hot or cold filtration. So that's what I always recommend the customer, to consider the possibility to purchase the full jacket vessel. The great advantage of the Druck filter from Asahi is that you can do the filtration under pressure. So, and the maximum pressure that you can have in this reactor, in this Druck filter, is maximum overpressure is 2 bars, which means that by default you can create the pressure difference of 2 bars, which doesn't mean that you will get a 2 times higher filtration speed, because that again depends on a lot of different aspects like particle size, filter material, viscosity of the filtering media and of the slurry, and so on and so forth. But this will be definitely quicker than filtration under vacuum, having the 2 bar difference, because well, because you have a 2 times higher pressure that presses on your slurry. So this is very important. Jacket pressure is a standard thing. It's up to 0.5 bar, and the operating temperature is -92 plus 220. Delta T for this kind of equipment is 110 degrees as well. When we're talking about filtration under pressure, it is always very important to keep in mind that we need some protection, because that's the glass and we are applying the pressure, so it can explode. So first of all, it is not pictured here just because we would like you to see the equipment itself, but equipment goes with a safety shield, so in case the unit will explode in some, I don't know, somehow something will go wrong and it will explode, it won't explode straight into your eyes. That is very important. And I think maybe that's the point that I should have started with. The equipment has the pressure gauge and the pressure relief valve as standard, and that's the accessories that are the must for this kind of glass equipment. So pressure gauge is something that you need to measure the pressure, that's pretty obvious. And the pressure relief valve, you can see it here. It is a spring-loaded thing, so I'm not sure if you can see that, but there is a spring in here and there is a nozzle here. So when the pressure increases up to 2 bars or higher, there is a certain glass part here which and the spring is calibrated, so when the overpressure occurs, this glass part slightly rises, releasing the excess of the atmosphere of the gas that we use for pressurizing, and so the gas is released through this nozzle, small nozzle. And as soon as the pressure goes below 2 bars, again, of course, this glass part closes back and isolates the system from the atmosphere, and so you can continue the filtration. Pretty similar thing, but the difference is that that's the filter dryer. The difference is that here we have a very thick bottom part. Why? Because we have a filter plate here. I will show you it in more details later on the next slides. But all the rest is pretty much the same. So just except for the last lines of the filtration part, that's the bottom part. You can use it for hot filtration or cold filtration, and of course you can heat it up when you're doing the drying. Of course you will have to heat it up. Before we will go to a detailed explanation of the glass parts, I would like to explain to you the advantage of the support stand. The great thing about Asahi is that they are doing the support stand that is a universal one, so you can use it for any kind of vessel that can be purchased from Asahi. Either that will be a double-walled reactor, or the filter reactor or filter dryer, or double-walled reactor with ring baffles, or triple-walled reactor, or this kind of triple-walled reactor with ring baffles, and so on and so forth. So you can use this support stand for any kind of vessel. That's really great because you can purchase one support stand and you can do the synthesis, and after that you can change the vessel and do the filtration or the extraction, or I don't know, maybe solid phase synthesis, and any kind of process that you need. That's how you save the money. There are two types of the support stands. Why so? Well, first of all, about the sizes. We have the DM100 support stand for the 1 liter and 2 liter filter reactors or filter dryers, and DM150 for 3 and 5 liter units. Why? Important thing is the internal diameter and the ratio between the diameter of the steering blade and internal diameter of the vessel. Why? Because the bigger the diameter of the steering blade is, the better it is. I will explain it to you why it is so later on, when I will show it to you the type of the steering blades that Asahi offers. But what is also important to mention, that you can easily and very quickly change the vessels from one to another. This is something that I usually actually show on the video, so that's the moment when I switch to the video. Let's go from the top of the reactor or the filter dryer, Druck filter, discussing the accessories. So first of all, one of the very important part of the filter is the type of the steerer guide that is used. This is something very unique, I would say, because this is the type of the steerer guide that can really work continuously under vacuum down to 15 to 20 millibars, even when steering. So this is very important. Let me show it to you in more detail. So on the left side of the slide you can see a relatively standard steerer guide that many of the manufacturers of the reactors offers. This kind of stereo guide is relatively cheap, and let's be honest, in some cases it can be used, but when we're talking about the continuous work under vacuum, there are two disadvantages, very important disadvantages, that this kind of stereo guide has. One of them is that, well, actually they are connected. So the problem is the seal that is in here, that is placed in here. When the stereo shaft rotates, and when you're doing the synthesis, for example, it rotates continuously for maybe 1, 2, 3, or 4 hours, or even more. When it rotates, the PTFE dust occurs. Well, not really occurs, it forms here. Why? Because the stereo shaft freaks over this PTFE seal that is in here. And although it sounds pretty strange, but it really happens like this. Why strange? Because PTFE is known as the material that is really good for this kind of friction parts, but it really wears out when PTFE rubs against PTFE. So there are some PTFE dust forming below over here, so below the stereo guide, and this PTFE dust falls, guess where? It falls straight into your reaction mixture of the slurry that you are filtering, and in this case, of course, you will never be able to get rid of it because that's PTFE. So that's the point number one. But again, this is something that should be pretty obvious when there is a friction, and when the dust forms here, the material goes from the stereo shaft and from the seal, which is in here, and it means that it gets not as tight as in the beginning, so you will lose the vacuum, because the seal is not a seal anymore actually. So this is the second problem. All of these two disadvantages are something that we can forget when we're talking about the great stereo guide that Asahi has. So due to the design of the stereo guide, there are no PTFE dust forming below. Well, it's not even below, not anywhere. Why? Well, first of all, because that the peak, that's the material, freaks against this glass tube, and due to the fact that these two materials, when they freak against each other, there are no dust forming, you will get no dust inside your reaction mixture or inside your slurry. This is the only type actually of they have the unique bearing in here, and the unique about this bearing is that that's the only bearing that I ever saw in my life which is made of PEEK. That's the kind of a brown material which you can have here, which you can see here is the PEEK, and it has some glass balls inside. That's really piece of art, I would say. So when you are talking about the process under vacuum, you will definitely need this kind of a stereo guide. And if you don't want any PTFE dust inside your reaction mixture or slurry, then you will again have to think about this kind of stereo guide. Flexible bearing coupling. Well, I told you that I will go straight down from the top, but let's get back a bit to the top. When do we need it? Well, first of all, it allows us not to center the overhead steerer. that precisely, as we'll have to do that without this kind of a flexible bearing coupling, because stereo shaft is not fixed in the chuck. There is a small steel part that we have in here, and when you raise the overhead stereo, it can be easily taken out of this coupling. So this is the moment actually when I switch again to the video, and I show it to the customers how it really works, the video that Asahi has on their web page. This is the first of all, well, not first of all, and when do we need that? Apart from the ease of disassembling the overhead stereo, you do not need to unscrew the chuck and take out the rod when you have a standard overhead stereo guide. Apart from that, you will be able to work with the viscous media, because due to this coupling you will have a lower load on a central joint, and so this prevents the central joint from breakage. And then and also you, from my opinion, this is the must when you're working with a slurry, to minimize the load on the center port of the glass lid as well. So manual steering, as I told you already, this is very important to keep in mind that you will need a proper size of the stereo blades. Why so? When we're talking about the filter reactor, when we're talking about the extraction, of course, you will do this for a certain period of time, like maybe for 1 hour, for 2 hours, and so on. So you will definitely need an overhead stirrer. But when we're talking about the filtration, when do we steer? First of all, of course, we need to steer to smoothen the surface of sediment to prevent the cracks formation. Why would we like to avoid the crack formations? Because when we have the cracks on the surface, then the air that actually presses the solvent through the filter cake will stop to push the solvent, and it will just leak through those cracks. So there will be no filtration anymore. So with this type of the stereo blades that has the diameter almost as big as the internal diameter of the vessel, you can easily smoothen the surface of the filter cake, and there will be no crack formation. I mean, well, there will be some crack formation, but you will smoothen them and fill them with sediment that is inside the filter. So you will have the efficient filtration. And the second point, why do we need it? When do we need it? We needed this kind of stereo blade when we need it when we do the replacement washing. What is the replacement washing? I think this is something that I should explain. When we do the filtration for the first time, so we load the slurry inside the filter, we do the filtration, we get rid of the most of the solvent, but of course there are some dirty solvent inside the vessel remaining, because the sediment is relatively pretty wet. So we add some additional solvent, pure solvent, which replaces, when we do the filtration, which replaces the dirty solvent, dirty reaction mixture. And in order to do this efficiently, we need to stir the filter cake with the solvent before we apply the vacuum and filter. So what we do after the first filtration, we fulfill the vessel with pure solvent. We do not apply the vacuum at that moment. We stir it, just maybe 2 or 3 or 4 maybe rotations, and we mix it actually, and then we apply the vacuum and filter it. So that's how it works. And that is why it is so important to have the I will go back to the previous slides with the support stand. And that's when you will understand why it is important to have different sizes. When we have different sizes, if we would have a size of 100 DN100 for the 5-liter reactor, for example, there will be two options. Either we will have to have, you can see here the picture of 2-liter vessel. So if we're talking about the 5-liter vessel, it will be 2 times higher, having the DN100. Because when we why so? Well, why so? It is pretty obvious, but when we have the steering blade, which has the diameter close to the internal diameter of the vessel, you will need to insert the steering blade somehow into the vessel. Well, in some cases maybe you can do that from the bottom, but it would not be that easy, especially when we have a very long vessel, and that would be a nightmare, believe me. So in this case you will need a bigger diameter, because if you will have here the 5-liter vessel with a big diameter here but DM100 here, then you will be able to insert from the top only the steering blade with a diameter of 100 millimeters, 900 or something like that. So that's why we need to have DN150 for bigger vessels. Maximum heat transfer area and minimum dead space. Well, this is a very important point, especially the point on the left side of the slide. The unique thing about the Asahi jackets is that when we're talking about the filtration and the vessels for the filtration, only the Asahi is the only manufacturer who has the full jacket design. Most of the not most, all of the other manufacturers has the design of the vessel when the lower part repeats the upper part. So for Asahi we have the full jacket, which means that the heat transfer fluid hits the media which is inside the vessel straight from the bottom, right from here. And when we're talking about the other manufacturers, they have the design of the bottom part equal to the design of the upper part. So if you rotate it 180 degrees, you will understand what I'm talking about. So in this case, when we'll have in case of the other manufacturers, when we're talking about the filtration or even maybe solid phase synthesis, you will never be able to heat up the bottom part. And depending on the volume of the vessel, this can be a relatively high volume, big volume. So for example, if I'm not mistaken, for the 5-liter reactor, let's say the dead volume, which is not heated at all, is something like, if I'm not mistaken, close to 500 or 600 milliliters, which is pretty high, I would say. And another point which is also pretty important is that the design of the flush valve and the bottom part actually is done with the minimum dead space, which is also very important. Another good thing, by the way, about this type of the flush valve, it has another nut, but actually that's the same valve that is used for the reactors. So if you have two of these valves, you will always have a spare, either for the reactor or for the filter. Easy to handle product and clean the filter. As I told you in the beginning of the presentation, when we're talking about the filtration, you will always have to keep in mind sorry, I forgot to translate this, but I think that's pretty obvious what is written here. I will explain it. So when we're talking about the filtration, it is always very important to keep in mind how you discharge the filter, because step number one is to get the sediment inside the filter, but step number 2 is to take it out. So when we're talking about the small vessels, small funnels actually, with a volume of 100 milliliters, it is not a problem, as mentioned already. But when we're talking about the bigger vessels, like 1 liter, 2, or maybe even 5 liters, you need to keep in mind to think about how you will discharge that. So first of all, the great thing about the standard scope of supply from Asahi is that you get this great lap jack, which is designed to support the bottom part of the filter. And so you can easily lower the bottom part with this lap jack. And before, of course, before lowering, you need to open this clamp. And it is important to mention that this is a quick release clamp, so it doesn't require any additional tools to take it out. Just you open it, and you can straight away lower the bottom part. So this is great. But also, this is another point, you can also lower the vessel itself together with the filter part, and you can take out not only the filter bottom but you can also take out the vessel itself. When do we need that? Well, we take out the filter bottom when we have just a small amount of the, I don't know, for example, maybe when a small amount of the substance here, for example, when we do the filtration of the process which was done with a solid catalyst, and then we have a small amount of catalyst here, or when we have a lot of slurry and we have a lot of sediment, then we need to take it out together with the vessel itself. Filter, the design of the filter bottom. So filter assembly consists of 4 parts. So part number 1 is the seal. Then we have the filter cloth, which can be a filter paper or polypropylene filter or PTFE filter or any kind of actually filter material that you can have out there in the market. And that's great advantage because you can easily purchase it locally, or filter paper is something that can be found in every lab actually, so this is really great. And then we have a sinter disc, which is made of PTFE, and it is used as a support plate because we have all those grooves in here to perform the filtration on the whole surface of the filter. So that's why we need this sintered filter as a support plate. So it is like this. So the design of this seal is made for the cases when we have the filter cloth which is relatively thin. When we have relatively thick filter cloth filter material, then we will need to have another type of the seal, which is also supplied in a standard scope of supply, which has this kind of a groove inside this seal, and you insert the filter material inside this groove, and you will, in this case, you will as well get the perfect sealing without any leakage. When I was talking about the discharging, I was saying that we can easily lower the bottom part. But what is also important to mention, that we can not only lower the bottom part, but we can not only the part together with the we can lower the bottom part together with the vessel, but we can not only lower the bottom part with the vessel, but we can also rotate the bottom part with the vessel, as you can see here on the picture. And this is the moment when I again switched to the video and showed the video where I think that was Fukutara. Yeah, that was Fukutara who was doing this kind of rotation. This is again very important and very useful tool, and this is something that is supplied by default with a filter reactor or a Druck filter or filter dryer. This really saves times and prevents the product loss when you're doing this kind of thing. In order to do the discharging process easier you will definitely need a lid holder, and you can easily see here why, because you don't need to disassemble all the upper parts. You can with the lid holder is this item here, so it holds the lid in a certain place. You just lower the vessel together with the filter bottom, you tilt it to a side, and then you can easily rotate the filter body to discharge the product. And there is also another tool, lift mechanism, which allows you to lower the filter vessel just by rotating this knob here. It is, well, let's be honest, it is relatively expensive, but it really helps you when you have a very heavy vessel, or maybe if you're a lady, then you will definitely need it to do it on your own, to do the lowering on your own. This is again the place when I switch to the video, because it is much easier to show it on the video what are these quick release couplings for. But in order to explain it in a few words, this is something that we need when we do this kind of things. Why? Because when we have a jacket, we also have hoses. And hoses, although the hoses from Asahi are very flexible and very light, they will still bother you when you will need to rotate the vessel, especially like this. So you need to disconnect the hoses, and in order to do that quickly, you will need these quick release couplings. So as I told you, I'll switch to the video in this place, and that's when everyone will see the advantages of these quick release couplings. I think there is only one point that I should mention here, is that the difference in the design of this part is that this is the pressure relief valve. Why do we need it? Because when we're talking about the glass reactor, and if the jacket of the glass reactor or glass vessel is filled with heat transfer fluid, and the heat transfer fluid starts to expand due to the temperature, the heat transfer fluid actually will break the jacket, and in order to avoid this kind of cases, you will need this pressure relief valve. So once it is calibrated to 0.5 bars, and in case the overpressure situation occurs in the jacket, then the overpressure valve will open, and it will release the excess of the heat transfer fluid, preventing the breakage of the jacket. Filter dry assembly. So when do we need and how it actually works? It is really simple in terms of the idea actually. So when we're doing the hot filtration or the cold filtration, we have the volume of the solvent here inside the vessel. So the heat or cold that is kind of generated, we get from the heat transfer fluid, enough to heat or cool down the media that we have inside, because the volume of the, as I mentioned, the volume of the slurry is relatively high. But when we're talking about the drying itself, there is no more solvent in here anymore. So we have only the sediment, and the amount of sediment can be relatively low, maybe like this, like 1 centimeter. And of course, in this case, the surface area which heats the sediment would be very small. In order to increase the heating area, we need something that would heat our sediment from the bottom, and that's the heated bottom. The connection design is shown here, so everything is pretty simple. No need to stop on that. So we heat up the bottom, we heat up the jacket, and that's how we get the efficient drying. When do we need the filter dryer? This was mentioned actually in the beginning of the presentation. So we need the filter dryer when we need to protect the sediment, the substance that we are filtering. from the exposure of the atmosphere, or from the apparator that can damage it somehow, or the other way around, to protect the apparator from the substance. So in this case we will get the dry powder in the end, and that is very important. Why do we have the overhead stirrer here? We have the overhead stirrer here, but not the manual stirrer, because if we want stir, we will have the pretty big size of the pretty big pieces of the dried media, and this is something that no one needs. Plus the filtration process, the drying process will not be that efficient, because we will already dry the lower part, but the upper part over here will be still relatively wet, and in order to to mix everything properly, and to replace the dried substance with a wet substance, like changing dry will go up and wet go down, then we need to stir everything. So this is why we need the overhead stirrer, which will continuously rotate the stirrer blades. So design of the heated bottom is, again, the idea is pretty simple, but the design is great, and actually this is something that no one's on the market offers. So again, we are with Asahi products are pretty unique with it. So it looks like this. So the filter itself, the material that is in contact with the media, is still PTFE, but we have this stainless steel insert, which and we pump the heat transfer fluid from this stainless steel insert, and it heats up the bottom. So here on the slide you can see how it works. So in the beginning we have a very wet sediment, and then we dry for a certain period of time, and then we get the completely dried substance in here. Additional accessories. This is something that not everyone thinks of, these kind of things, but again, this is something that is really important, and that's the receiving vessel. Asahi has a receiving vessel with a volume of 2 liters, and it is very important that all the connections that we have here are made of PFA or PTFE, which makes this design absolutely chemical resistant. So the connection is relatively simple. It easily connects to the bottom part. This is actually, although it looks and sounds pretty simple, a lot of customers asks about that. How do we connect that? How would that be a chemical resistant one or not? Because not everyone offers that. Going back to my experience, I can tell you that one of the most difficult thing when we're talking about the reaction systems, and when we're talking about the filtration systems and any kind of this kind of things, equipment, the most difficult thing is to connect one equipment, one unit to one type of equipment to another type of equipment. For example, one of the standard mistakes when we're talking about the combination of the reactor and the thermostat is the lack of the adapters that are needed. For example, when we purchase a 1 liter reactor which has an M16 thread on the jacket connectors, and we purchase the reactor triple wall for low temperature synthesis, most of the, for example, Huber unistats, or it doesn't really matter, any other units like from Lauda or from Ulaba, for the lower temperature thermostats, they have a thread of M30 on the thermostat. So when you purchase the thermostat, you purchase the reactor, you definitely purchase the hoses. If you purchase the hoses from Asahi, you will purchase the hoses with the M16 thread. And you always need to keep in mind that you need adapters from M30 to M16 thread. Otherwise, when you will start to do the installation, you will have some problems, because you will have everything except for the adapters. So you will need to buy them, you will need to get back to the customer side, and so on and so forth. So when we're talking about the hoses, when we're talking about the connections, it is always very important to inform the customer that they will get the perfect solution. They will get the chemical resistant solution, they will get a tight solution that will work under vacuum and under pressure as well. So this is the connector. We connect here the vacuum hose and the vacuum pump. So this is the universal receiving flask that can be used for notch filter or for Druck filter. I forgot to change the name. For the filter dryer as a receiver, or for the filter reactor. Pilot units. Well, actually, we discussed most of the accessories and advantages, and for the benchtop units, and they are pretty much the same for the pilot units. The pilot units are just bigger. So, like for example, you can see. Let's go into the next slide. So you can the processes that can be done in these reactors are the same ones. So for the filter reactor, you can do the filtration, you can do the synthesis, extraction. For the Druck filter, you can do the filtration under pressure. For the filter dryer, you can do the filtration under pressure and drying afterwards. Filter reactor. Standard vessels are 10, 20 and 30 liters, but you can also have bigger ones. Design is pretty much the same in terms of the characteristics. So you have the except for the operating temperature, it can go down to -90. So in terms of the design, the difference is that we have a little knob here, over here, that can be rotated, and by means of the rotation you will lower the bottom part. So there is no lap jack here anymore, because the unit is pretty big, and so there is a lifting mechanism inside the support frame, and you can easily lower it, either just the bottom or the bottom together with the vessel itself. So this is the good thing about that. And you also have all those kind of glass parts in here, which are used for the glass condenser can be used for the condensation or for the distillation. And this is the receiver. That's the dosing funnel, and that's the pressure relief valve and the pressure sensor and overhead stirrer. All the other advantages and accessories that are available for the benchtop, available also for the pilot filter reactor, but just with a bigger size. Druck filter, again, very similar design. I mean, there's a very similar idea, but just a slightly different design. You can do the filtration under pressure. You can lower the bottom part, either just the bottom part or together with the vessel. And it is important to mention that the safety cover is included as standard. It is just not shown on the picture here. Filter dryer, pretty much the same like the Druck filter, but it just has the heated bottom. And of course you can get the customized solution, so you can have the 100 liter, up to 100 liter jacketed filters, and up to 300 liters non-jacketed versions. Here you can see that there is a certain design with the possibility of rotating the vessel by means of that little knob here. Well, not really little, but knob. And when we're talking about the big filters, you can also have this kind of cart, and you can easily take out the vessel by means of that cart, which can be lowered in order to take out the vessel. So this is the real example. That's the project. Very interesting actually project, which really shows that you can find the project where you would never expected it to find. there is a manufacturer in Russia which is called the Russian Caviar House, and which is pretty obvious what it does. It manufactures the it manufactures the caviar, black and red caviar. It is actually the biggest manufacturer of caviar in Russia, with the total budget, total with a total turnover of about I think something like 10 million euros per year, and they export a lot of black caviar for eating. They also sell it inside Russia, of course. But what they started to do is they started to manufacture the premium cosmetics based on the black caviar. They what they do is they do the extraction of different kind of fats or peptides, proteins from black caviar, and after that they use them to manufacture the cosmetics. How do they do that? First of all, as I told you, they do the extraction. So they have the black caviar, they crush it in a mixer, and then they load it into the jacketed filter reactor. They add the methylene chloride inside the vessel as well. They heat it up to something like plus 50, as far as I remember. Stir it for a certain period of time, and then they filter it. So, as I told you, this is a typical application for the filter reactor, the extraction. Another thing that they do the cold filtration. They do the cold filtration under vacuum in order to get rid of fats. Why? How do they do that? There is some certain amount of fats that they would like to get rid of. So they get the solvent, the solution of which they got after the extraction. They put it inside the fridge and cool it down to something like minus 10 degrees centigrade. Then they cool down the vessel itself. When they cool down the filtrate, the fats get solidified, and then they can be easily filtered. And that's why they need the cold filtration, because without the cold filtration, without the cooling down the jacket, the fats will dissolve. I mean, they will start to melt, and they will not be able to perform the filtration. So, very important, very interesting application, and quite unusual one. What I would like to show you actually on this slide here is kind of a promotion, let's say, a very small and nice vacuum pump from I call them Ilmvac, because that's how they were called initially, but then now they are Welsh Vacuum, but in general they were purchased by Gardner Denver. So this is a very small unit for very small chemical resistant vacuum pump, which has the small knob which can control the vacuum, and the small vacuum gauge here. So and a small protection vessel which protects the vacuum pump. So very small one, and I do recommend this for this kind of applications. Another application, I'm not sure if that's the right word to be used, cascade system, but that's how we call it here in Russia. That's the cascade system, which consists of 2-liter jacketed reactor. The customer does the synthesis here at plus 180, and 2-liter filter reactor that is used as a notch filter for hot filtration at plus 70. So it's not really very well seen here on the picture due to those rods of the fume hood, but here we have the connectors that connects the outlet of the reactor with the inlet. Here we have the adapter, and this you can see maybe here the PTFE tube which goes inside the filter. So when we apply the vacuum, to the system. Unfortunately, the receiver is not connected here now because it was under cleaning. The system was under cleaning when I took this picture. So you'll have the receiver here, 2-liter receiver, which is connected to the vacuum pump. When we apply the vacuum to the receiver, we will have the vacuum here, and due to the vacuum, when we open the bottom valve, the slurry will start to flow from the reactor straight to the filter reactor, and that's how we do the filtration. Okay, we are done with the filtration, a very big part of the, I call it the post-treatment of the reaction mixture. Now I would like to talk about the distillation, evaporation, and concentration. So, what kind of equipment Asahi offers for these processes? Asahi manufactures actually almost all type of the equipment that can be used for this kind of processes. They manufacture rotary evaporators, thin film evaporators, short path evaporators, and rectification columns. Some calls them the distillation columns. What is important when you choose the unit to do the evaporation? First of all, you need to know, of course, the volume of the solution that you would like to evaporate. Second point, what kind of solvents you will have inside the media that you plan to evaporate, and of course you need to know the solvent's boiling point. What is the temperature difference between two components to be distilled? I will explain it later on why it is important. Do we need to evaporate till dry, or we need to just to concentrate the solution? Is any of the component thermoliable? Liable is that, I hope that's the right pronunciation. What is the viscosity of the mixture that we need to distill? And what is will the mixture foam when distilled or not? A lot of words on this slide, but that's important points and advantages and disadvantages of each method, because you will be able to choose a proper method by knowing the advantages and disadvantages of the method. So when we're doing the rotary evaporation, what are the advantages? Well, rotary evaporator is relatively cheap unit, and it is possible to distill foaming mixtures. Disadvantages that we can separate components with a very close boiling point. So the delta T, if we're talking about the separation of the solvents which has the difference between the boiling points less than 20 degrees, then you will definitely should not use rotary evaporator. You will not get a sufficient separation of one solvent from another solvent. There are some other tricky things about azeotropic mixtures. Even, for example, even if you are trying to distill ethanol and water, you will not be able to separate ethanol from water because they create the azeotropic mixture, and that's why you will never be able to get the 100% alcohol by this kind of distillation, neither on a rotary evaporator, nor on a thin film, nor even on a rectification column. There are other methods for doing this kind of things, for doing this kind of separation. So this is important to keep in mind. Second point, with a rotary evaporator you cannot evaporate thermoliable substances. Why so? I will explain it on the next slide. Point number 3, difficult to arrange continuous evaporation. There are some rotary evaporators and some accessories on the market. As I'm making a demo version of the webinar, I think I can mention them. Well, first of all, we have Buchi with their R220 continuous modification of the 20-liter rotary evaporator, and we also have the Distimatic unit from Heidelberg. Both this thematic unit from Heidelberg is I would say it is relatively complicated unit, and from my point of view, it still has more questions than answers. There are two types of the modifications of this thematic, and uh, the well, okay, let's not go deeper into details about these two items. But as far as I know, these are the only units on the market. I mean, this thematic and R220 Pro continuous, then can do the continuous evaporation. Uh, Point number 4: we cannot distill viscous media, so that's the disadvantage for the rotary evaporator. Thin film and short path evaporators. The idea of both of them is the evaporation in a thin film. That's why I've combined them in one table, but we can easily split them into two tables because there are some difference in the technology of these two type of the equipment. So advantage of the evaporation in thin film evaporator or SPE. Advantage is that we can easily distill thermolabile mixtures. We can also distill viscous media. It is possible to separate high boiling components. Possible to work under high vacuum down to 10 to the minus 4 millibars. And it is possible to arrange the continuous distillation. Again, the last point is the advantage of companies like, again, let's be honest, companies like VTA, because they have their own, they have the pumps of their own design that were designed to work under vacuum, not only for loading but also for discharging, which is obviously the must when we're talking about the continuous distillation. But when we're talking about the thin film evaporators, I had an experience with offering the peristaltic pump for loading the thin film evaporator, and I will show it on the pictures later on in this presentation of how it was designed, and it worked. So the disadvantage of the thin film and TFE and SPE. So first of all, that's the expensive equipment. Point number 2, we have the problems with distilling foaming mixtures because it will create the foam inside the heat exchanger. We cannot evaporate till dry powder, but we can do this in rotary evaporator, obviously, and we can separate close boiling components with delta T less than 20 degrees. Rectification column. Advantages: it is possible to separate substances with boiling points difference of 4 or 5 degrees. It is possible to arrange automated fraction collection, which is also great. This is something that we cannot really arrange in a thin film TFE, SPE or rotary evaporator. But the disadvantage of the rectification column is that it is again relatively expensive. It's used only for liquid substance separation, so you will not be able to separate solid from liquid. Oh, well, let's put it this way: we can separate liquid from solid, but only in cases when we do not need the solid at all. So we will throw out the solids or the residue that we will have in the evaporating flask. And for the rectification column, I would say that it is pretty complicated thing in terms of the calculation, so you'll need a lot of calculations to be done before you will be able to choose the proper size of the column, to choose the proper packing material for the column. So here are the pictures of the unit: rotary evaporator, TFE, SPE, and the rectification column. The size. The size of the rotary evaporators that Asahi offers is 20, 30, 50, 100 and 200 liters. Condenser type, ascending, descending, bath temperature. standard range, so water bath up to 90, oil bath up to 180. There is a handling cut option, which I will talk about on the next slide. And what is important to say that Asahi is well, it says that only available in Asahi glass, but I know that QVF, the Dietrich, manufactures them, the 200 liter rotary evaporators as well. I don't know if they do manufacture them up to now, but I saw one of them with my own eyes when I was visiting their plant in, that was 2011, I believe. So there is one thing that I would like to mention about the Asahi evaporators, the capacity. What is great about Asahi, and what I do like about Asahi, that unlike all the other manufacturers, Asahi is really ready to how to say that in the proper words, Asahi is really ready to fulfill the crazy requirements of the customers. And I had a project which I was told that Ikeda-san was not didn't really believe that we will be able to sell that unit together with Shinga, but we did. There was a 6-liter explosion-proof rotary evaporator that was sold in Russia, and it has a very complicated cooling, how to say, the cooling system. So it has 3 types of cooling, so 3 receivers. I don't want to go deep into details. I can show it on. I can show it if that is really required, but it is really great. So when we're talking about the capacity, again, when we're talking about standard units, it goes from 20 to 200 liters. But Asahi can manufacture even small things, and even in explosion-proof version. Rotary evaporator. So why rotation? It turns out that not many people out there on the market, even chemists, really understand why we need the rotation. Well, first of all, sorry for the picture of Buchi. It can be changed with another one. I was using this presentation as well as this picture for the presentation for our company, and as you know, we are distributor of Buchi Labortechnik. So why do we need the rotation? What is the advantage of the rotation? When we're talking about the standard evaporation, let's imagine this is the I don't know, water bath and the flask, and the evaporation surface is here. The evaporation speed depends on the evaporation surface. So the higher the surface is, the quicker evaporations occurs. So when we have a stationary flask without rotation, the surface is only as big as this one. So, but when we rotate the flask, when we start to rotate the flask, the solution that we have here inside the flask will start to wash around the surface of the flask. So the total evaporation surface will be now like this one. So it is 2 to 3 times higher. It has 2 to 3 times higher surface than the stationary flask, and obviously the evaporation speed will be 2 to 3 times higher. So in general, the process is pretty simple. So we have the heating bath, which heats up the flask. We have the evaporation mixture here. We have the vacuum applied to the system in order to lower the temperature, the boiling temperature of the solvent. So when we apply the vacuum, the vapor starts to form, and they go through through this evaporation tube straight into the condenser. where we'll have the condensation process. The condenser has the coil, which is cooled down by means of the tap water or the chiller, and we have the condensate, which condensates on these spirals, and they go straight into the receiving flask. Here we have the receiving flask for the condensate, actually for the solvent that is condensated. That was an explanation of why do we need the rotation, as I told you. When we're talking a big evaporators with a volume of 50 liters and higher, not many customers think about that, but when we're talking about 20 liters, you can still operate with a 20-liter rotary evaporator and with the 20-liter evaporating flask with your own hands. But 20-liter evaporating flask already itself weighs about 4 kilograms. And imagine that you have something inside the flask. Let's say you have, I don't know, 4 kilograms of powder that was dried inside the flask. So in total it is 8 kilograms, which is relatively heavy. And if you are a lady, it is not that easy to operate even with 8 kilograms in your hands, especially if it is slippery because you use the oil bath, for example. But when we're talking about a 50-liter flask, it is absolutely impossible to operate with your own hands. So because the flask itself will be maybe 8 kilograms, and imagine you have the 10 kilograms of powder or maybe 20 kilograms of powder inside, so you will definitely need some instrument to operate with a flask, and this is when you need a special cart. It looks like actually like this. It is pretty simple. It's on the wheels and it has some kind of arms here that are controlled with a knob which is on the side, and just like the arms, they can open or close when you need to fix the flask, and they can also rotate like here in order to do the discharge of the product from the flask, or maybe for washing purposes and so on. Another points that the customers do not really think about, but this is something that really, creates the image of the brand. It really gives you a nice feeling that the manufacturer really thinks about you. The additional small but so important accessories. First of all, the external shower. When we're talking, let me get back to this slide. When we're talking about the big rotary evaporator, I believe this one is 100 liter or 50 liter. So you can clearly see that even when you lower the flask, well, not actually lower, you raise the bath, there is a very big surface that is open to the air, surface of the evaporating flask, and obviously when you start to rotate at a relatively low speed, then there will definitely be not in the solvent, that is the mixture that is washing inside the flask, will cool down and will not evaporate from the upper surface. In order to keep the evaporation at a proper speed and in order to keep the upper part heated, Nasahi offers a special shower. You can see it here. It takes out by means of a very small pump, it takes out the liquid from the bath, and it pumps straight onto the top of the evaporating flask, heating up the flask with the media, either that's the hot water or hot oil. It heats up the upper part of the flask. So this is important to keep the speed of the evaporation at a proper level. And what is also important is that, and this is something that I saw only at Asahi, the sampling port. In order to take the sample from the receiving flask For example, you are drying, let's imagine something that should be pretty typical. You are drying the powder, and you need to understand, you need to know at a certain moment, either we can stop the drying process or not. How can we do that? We need to take out the sample and measure the amount of the solvent that remains inside the powder. For other manufacturers, we need to disassemble the flask, take out the sample, and then assemble the flask again back. For Asahi, we do not need to do this. We just need to open the sampling pot, which is made in the evaporating flask, and this is a unique thing. You open the sampling pot, you take out the sample, you close the pot, and you continue the drying process. Thin film evaporators. Oh, sorry, yeah, again, forgot to translate it into English. So, for the lab thin film evaporators, there are two sizes, DN60 and DN100. Evaporation surface is 0.05 square meters and 0.1 square meters for DN100. Operating pressure, atmospheric pressure down to 0.1 millibars. Max temperature up to 200, and as an option we can have up to 300. We have the feed rate as shown here on the slide, and the rotation speed up to 400 RPMs. The thing about that, well, I think the problem for the rotary thin film evaporators and for the short path evaporators, the main problem for them is that not many people really understand when and why do they need this kind of equipment. As I told you already, it is relatively expensive comparing to the rotary evaporator. So if you compare the similar performance rate, the thin film evaporator would be something like maybe 3 times more expensive than the rotary evaporator. So when do we need the thin film evaporator? Let me explain it to you by explaining you how it really works. So the process goes like this. So you feed the feeding vessel with the mixture that you need to distill. So you feed it in here, then you open this valve, and the mixture will start to drop down into this heat exchanger. Inside the heat exchanger we have the wipers that rotates by means of the overhead stirrer. You can see it, you can't see it here on the picture, but it is here. It is mounted here on the support frame. So the wipers rotates here, and the mixture that we have, by means of the wipers, they are spread along the walls of this heat exchanger. The central heat exchanger is heated, it has the jacket and is heated by the thermostat by means of the heat transfer fluid. As the thin film that is formed by the wipers is really thin, we have almost immediate evaporation of the solvent from the walls, and the mixture, by going down along the wall, loses almost all of the solvent. So when it loses most of the solvent, we have the condensate gathered here in the receiving flask, and the vapors of the solvent, they go into this condenser, they condense here, and we collect them here in the receiving flask. So the first disadvantage, well, let's start with the advantages. So the advantage is that we can easily evaporate the thermolyable substances. Why? Because the time the mixture is in contact with the evaporating mixture is in contact with the heat exchanger is relatively low. It is actually by let's say the gravity. Depending on the size, it can be, I don't know, 2, 4, maybe 5 seconds, up to, I would say, up to 10 maybe seconds, depending on the viscosity of the media that you are inserting. So that's the advantage. You can easily concentrate the mixture of the thermolyable substances. Why can't we do this in rotary evaporators? Because according to this picture, you will always have a direct contact of the substance with a heating bath. Either that will be water or oil, doesn't really matter. The substance will be always heated. This is the problem for the rotary evaporator. That's why you cannot evaporate thermolyable thermolyable compounds in the rotary evaporator. There is another actually way of evaporating till dry. Yeah, well, let's get back to this slide. So the advantage is also a disadvantage. Why? Because we cannot evaporate till dry. Because if you will evaporate till dry, then the dry substance will form on the walls. First of all, it won't fall down. Secondly, it will start to decompose on the walls. So for this kind of applications, when we need to evaporate till dry something that is thermolyable, there are another type of equipment that is called freeze dryers or spray dryers. But this is another story. Asahi doesn't manufacture that, so I'm not going to go deeper into this kind of equipment. Another advantage of the thin film evaporator is that we can evaporate high viscous mixtures. Why? Because, well, first of all, let's start with the rotary evaporator. Why can't we evaporate the viscous media in rotary evaporator? Because, well, to some extent we can do that, but the problem is that the viscous media will not flow around the flask and will not form this kind of thin film around the flask. So viscous media will stick to the bottom part of the flask and it will rotate together with the flask. So the evaporation surface will be still relatively small. Plus, the problem is that when this viscous media will start to rotate together with the flask, it will not even be heated continuously. So it will be heated, then when rotating it will be cooled down by the ambient atmosphere and it will go like this, and so it will not be efficient at all, the evaporation in the rotary evaporator. So with a thin film evaporator, as well as with a SPE, short path evaporator, the great thing is that we can have the dosing feeding flask jacketed, and in this case we can heat it up. We will have the viscous media heated, and the viscosity of the media then by heating will go down, and so then we can easily open the valve and dose the mixture straight to the heat exchanger where we will have the evaporation. So that's how it works. Great thing about the TFE from Asahi is that it can be easily disassembled without any problems. You can easily change the wipers. The standard ones are made of PTFE, and for the high temperature processes you will have the PBE. They can work up to 300 degrees. Cleaning of them is really easy because you can easily take them out. So this is really great unit in terms of the operation. Asahi also manufactures not only small lab thin film evaporators but also the industrial ones. With an evaporation surface up to 1.5 square meters, internal diameters up to DN 450, and I took the rough performance for this size up to 1. Let me remember, I think that was for 1.5 and DN 450 TFE. So the performance is like this. Like for N-heptane you will have 120 kilograms per hour. Important to mark that emphasize that it is measured in kilograms, so in liters it would be even higher because the density of NHIP10 is lower than 1. So it looks like it goes like this. Yeah. Here is the example of the industrial thin film evaporators that was again sold here in Russia. The size of it is relatively small, actually, one, although it looks pretty big. It is 4 meters height and high, and the size of the heat exchanger is only DM100. So you can see that we did the complete engineering of the system, so we offer the complete solution to the customer. And again, this is very important in order to get the project, to offer the customer not just the thin film evaporator, but to offer a complete solution. So what we also have here, apart from the thin film evaporator, well, first of all, of course, we have the loud thermostat over there in the back, the small one, which is heating the main heat exchanger. We also have a vacuum pump from Vacuum here. We also have the dosing peristaltic pump from Masterflex. You can see the big 50-liter dosing flask here, and the injection point into the thin film operator is on the top over here. So there were two options. Either we should put the flask up to the top, but then we will have a problem with feeding the feeding flask. Or we could put, and another problem was that we will need to control the dosing speed somehow, and there was the only option was a standard manual valve, and then we will need a stair to get up to the top to control that, and so that would be a nightmare. So what we did, we put the flask in here, and we had the peristaltic pump, which was pumping the liquid from the feeding flask up to the top, and then the evaporation was occurring in the heat exchanger. And of course we have the cooling machine, the chiller, which was cooling down the condenser, which you can see here. And there was a secondary condenser. It can be slightly seen here at the back, which was protecting the vapors from the receiving flask to go straight into the vacuum pump. Another point, by the way, which is important, small thing, but it is very important for a convenient operation, is this little knob here. So by default we have the we have the drive here on the top, and the problem again was the control of the speed. Either we need a stair, or we talked about that with Shingo, and we have this, I don't know how to call it properly, this kind of flexible rod or flexible coupling, and a little knob here, and so it transfers the rotation from here straight to the drive, and so we have the knob in a comfortable position for the operation. So that was small but very important point. Short path evaporators. Sizes I mentioned here. The sizes are actually similar to the thin film evaporators. The only difference for the SPE in terms of characteristics is that we can walk down to the 10 to the minus 3 millibars. But I have to tell you that thanks to, I don't know, genius of Asahi's engineers, we've managed to sell one unit which was walking down to the 10 to the minus 4 millibars. And that was actually the main point why AGI EQUI SPE was chosen against VTA, which was offering 10 to the minus 3 millibars unit. The idea of SPE is very similar to the idea of TFE. So we have the feeding vessel, we have the heat exchanger, but the difference is in here. What is the difference? So when we're feeding the heat exchanger, we have the substance going along the wall, but in SPE we evaporate the substances with a relatively high boiling temperatures. So it is not like with the TFE when we have let's say maybe solid substance dissolved in a certain solvent. We might have two different substances with relatively high boiling points, but still we need to have some difference between the boiling points. So here we have a very high boiling point component, which is still going along the wall, and it is collected in this receiver. So let's call it the heavier component. A lighter component would start to evaporate from the wall, but let me get back to the picture of thin film operator. Some would say that we can do this thing in the thin film operator as well. Well, we can, but the problem is that with the as I told you, we're trying to separate two high boiling components. So although the other component is slightly lighter than in terms of the boiling point than the first component, but still when it evaporates from the wall, it will not be able to get to the condenser, because the path that this component needs to pass is too long. So it will start to condense straight on the wiper, and it will still fall into the receiving flask of the thin film operator. That is why we need the short path evaporator. Why it is called short path? Because when the lighter component evaporates from this surface, it condenses on the, I call it the finger condenser, which is inside the heat exchanger, actually located inside the heat exchanger. And due to the design of this insert, the lighter component condenses on the this finger condenser and goes along this wall and is collected here in the other receiving flask for the lighter component. We might have some residual light solvent which is afterwards collected in this cold trap, and there is a third receiver at the backside. I do hope that I explained this properly. So why do we need a higher vacuum? Because we're trying to operate the high boiling components, so that's why we need to high vacuum in order to lower the boiling point of the components. As well as with a thin film operator, we can have a jacket here in order to operate the viscous media, and that's the advantage. And in this case, actually, for the SPE, we do not have this disadvantage of evaporating till dry, because we do not need to evaporate till dry. We're trying to separate two liquids here, two liquid components here, and so that's how the short path evaporator works. It is pretty well known, I think, that short path evaporator is used for the cannabis industry, but we are not talking now about the real applications for the short path evaporator or thin film or any other. So we will skip this discussion. We are pretty close to the end, actually. So what I would like to show you is the short path evaporator, a customized one. Very interesting unit because it not only has a jacketed vessel here, feeding vessel here, which is heated by a separate thermostat. This thermostat is heating the main heat exchanger, but also the lower part of the heat exchanger is also heated, because the customer was really afraid that the substance that was the heavier substance may stick inside the heat exchanger. So that's why they have the jacketed bottom part. And as I told you, we are going down to the 10 to the minus 4 millibars. That's why we have this diffusion pump system together with a 4 vacuum, which is created by the rotary vane pump. I guess that's the last slide. So rectification columns. As I told you, I don't want to go deep into the details because this is something that is pretty specific. But I would like to mention these products because they are manufactured by Asahi and they are really great. And we also managed to do one of the project. We sold the rectification column, quite a big one, for a very specific application, and it was actually automated one. So general design. So first let me remind you about the idea of the rectification column. So when do we need them? We need them when we are trying to separate components with a very close boiling points. The difference can be, let's say, 4 maybe 5 degrees. That can be isomers, for example. So sizes. The sizes varies with the diameter varies from DN20 to DN200, height up to 2 meters, roughly 3 to 50 theoretical plates. That's the theory that you need to know in order to choose the proper column. Working pressure from atmospheric down to the 10 to the minus 3 millibars, working temperature up to 250. We can have a different control types, starting from manual ones with a manual valve that allows you to take a certain fraction, or you can have automated system with automated sampling by means of the solenoid valve and the controller, or you can even have a automated fraction collection by means of a 6-way valve, for example, which can collect up to 6 fractions or more if you have a bigger valve. There are also some options like vacuum jacket for the column or galvanized vacuum jacket. Vacuum jacket is needed in order to keep the temperature at a certain level. So this column section is without a jacket and this one is with a jacket. So thank you very much for your attention. It took me longer than 2 hours because I was talking in English. So maybe if you would like me to do this kind of webinars or presentations to others, maybe it makes sense to separate the separate this presentation into 2 blocks, like for example one was for the filtration, another one for the evaporation. And if you manage to listen this till the very end, well, then it means that I didn't spend my time in vain. Thanks everyone who managed to listen until the end.